Suppose we have y as a function of x. We can simplify this by creating a new variable, u, which is a function of x, and then expressing y as a function of u. Let's return to viewing y as a function of x. Let us change the color of the graph so that it represents the slope at each point of the graph. Notice how the upward slopes get more and more red each cycle. Red indicates a large positive slope. The slope at each point in the graph is dy divided by dx. That is, the slope at each point is the small incremental change in y when x is increased by one small incremental unit. Let's now view u as a function of x. As before, let's change the color of the graph so that it represents the slope at each point of this new graph. Here, the slope at each point in the graph is du divided by dx. That is, the slope at each point is the small incremental change in u when x is increased by one small incremental unit. In this graph, the slope at each point is given by the following equation. This equation indicates that as x keeps increasing, the slope also keeps increasing. This corresponds to how we see the slope increasing in the animation. Let us now view y as a function of u. Let us again change the color of the graph so that it represents the slope at each point. The slope at each point in the graph is dy divided by du. That is, the slope at each point is the small incremental change in y when u is increased by one small incremental unit. The slope at each point is given by the following equation. This equation indicates that as u increases, the slope keeps oscillating. This corresponds to what we see in the animation. When u is 0, the sine of u is equal to 0, and the cosine of u is equal to 1. Therefore, when u is 0 at the beginning of the graph on the left, the value of y is equal to 0, and the value of the slope is at the maximum value of 1. This also corresponds to what we see in the animation. Let's return to viewing y as a function of x. The slope of this graph at every point is how quickly y changes when x increases. This is equal to how quickly y changes when u increases, multiplied by how quickly u changes when x increases. We call this principle the chain rule. In this particular example, if we substitute the values for dy divided by du, and du divided by dx, we get the following expression. In this particular example, this is our expression for the derivative of y with respect to x. The expression for u as a function of x and the expression for y as a function of u do not need to be limited to the ones in this particular example. U and y can be any functions for the chain rule to work. And the chain rule is just one example of a much more general principle. Many apparently difficult problems in life can become very simple to solve once viewed in a new perspective. More information is available in the videos Polynomial Derivatives and Product Rule for Derivatives. Please subscribe for notifications when new videos are ready. Special thanks to all the people supporting us on Patreon. Your support is very much appreciated.